Alrighty, welcome back. So hopefully you had a chance to watch the paper chromatography video, and I'm just going to review some of the things that you learned there. So for an example, for our paper chromatography, here's our setup. A student performed an experiment to separate the pigments of purple ink, and as you saw, the purple ink, or any ink, is going to be composed of all different color inks, all different molecules. The first time she recorded her results, the water had soaked up the paper 5 centimeters past the baseline, where the spot of purple was initially placed. So this drop of the purple is right there. And eventually your solvent's going to move up, and your first line, or the red color, traveled 3 centimeters up from the line at that time. Alright, what are the mobile phase and the stationary phase for this process? The mobile phase is just that. It moves. It's the thing that moves. So that's going to be your solvent. In this case, we're using water and ink, so that's going to be the water. The stationary phase doesn't move, and so that's the filter paper in this example. So, mobile phase moves through the stationary phase in which the sample is dissolved. And here, it's water. Okay, our stationary phase then is the phase that doesn't move. Here it's the filter paper. And this doesn't move, and the sample also adsorbs onto it, so it kind of sticks to the top, kind of like we talked about the adsorption earlier of gases over certain metals. This is the phase to which the sample is adsorbed. Here, in this example, that is the filter paper. Alright, what properties do the red and blue pigments have that cause the opposite phase? So, here you're really looking at the difference in the strength of the intermolecular forces with the mobile phase, which is solubility, and the stationary or adsorptivity. Those differences result in traveling different distances. So red's going to travel further because it has stronger intermolecular forces with the solvent than with the paper. So it's going to interact more strongly with the solvent, so the solvent is going to carry it farther. If you're moving less far, if you're not moving as far, so in the example of the blue, the intermolecular forces don't interact as strongly with the intermolecular forces of the liquid. So, the difference in strength of the IMFs So again, the red travels further because it has stronger interactions, stronger intermolecular forces with the solvent than with the paper. Another good way to think about this is the polarity. So if you have paper that's very polar, and you have a solvent that's very nonpolar, if you have part of your mixture that is nonpolar, it's going to interact more strongly with the liquid solvent, because nonpolar and nonpolar likes dissolve likes. So the nonpolar part would move farther up here. If the situation was reversed and you had something where the paper or the stationary phase was more nonpolar, the reverse would be true. Alright, let's go to the next page. Calculate the RF value for the red spot. So the RF value, as you saw in the video, is just a ratio. So RF is equal to the distance traveled by the sample over the distance traveled by the solvent. So distance by sample over distance by solvent. And you could see that here in this previous page. So if this was our plate, if this was our paper, and this is the solvent front, so right here, this is going to be the line. This is where you would see it wet, and this is where the spots are. These are where the samples are. So, for example, we're going to look at red. The samples traveled 3 centimeters, but overall, all the liquid, all the solvent went up 5 centimeters. And you can see a wet line at that solvent front. So what we're going to do here is just plug in those numbers. So distance by sample, we're looking at red. Oh, that was 3 centimeters. So 3 centimeters on top. And then overall, the solvent front, the distance that the solvent traveled, that's going to be 5 centimeters. So 3 divided by 5. The RF value is 0.60. That's it. The RF value for the blue dye is 0.4. How far did the blue dye travel while the water soaked up to 5 centimeters past the baseline? So, let's plug it in. So RF of blue equals the distance of blue over 5 centimeters. And we know that the RF value that's given is 0.4 equals 0.4. Please pause this, find the distance that the blue dye traveled, and then come back. Alright, so after doing a simple calculation, you can see that the distance that the blue dye traveled is 2 centimeters. So we've calculated now this distance here as 2 centimeters. Later, the water had soaked up the paper 10 centimeters past the baseline, a further 5 centimeters from the first time. How far would the red color be above the baseline now? Let's calculate. So, the RF value of red equals the distance that red traveled over, now we have 10 centimeters past the baseline, so 5 plus the original 5 is 10. So 10 centimeters. And we knew the RF value of the red was up here at 0.60. And so the distance that the red will travel overall is 6 centimeters. So you can also do this on a larger scale. Paper chromatography, that was great for if we have tiny samples to separate, because you can only put a little dot of something on paper. So if I literally just drew a little dot right here and I wanted to separate what was in that dot, paper chromatography would be great. But if you had a larger sample size, several milliliters for example, you can do the same kind of thing with column chromatography. So this separates a mixture based on each component's ability to dissolve in the mobile phase versus adsorb in the stationary phase. The one with the greater solubility travels through the column faster and is eluted, that means like comes out, while the component with the greater adsorptivity moves through the column more slowly and is eluted later. So it will stick to what's in the column. So this is a column, and here you're going to, it almost works like a titration burette. You're going to pour things into the top and watch them come out the bottom. So the column is packed by using some material, and the materials really vary. So you pack it with something solid, and then you wet it down, and then you put your mixture that you want to separate inside the top. And then overall, that mixture is composed of different things. Now you can kind of see, as time moves on, the components separate. And this component is more soluble in the liquid or the solvent, so it's going to come out sooner, and you can catch that right here. And then eventually this part's going to move down. You can catch that separately. So that's the end of the second part of these notes. Please go watch the cool chromatography demonstration. It's a little bit long. Definitely worth watching the entire thing. And then please come back. And, before you go, as you watch, this isn't notes that we're going to write down. So you're going to summarize the video here. This is a spot for your notes. So go ahead, finish that video, and then come back for the next part.